I'm going to demonstrate the product rule for finding the derivative of the cubic root of x times the cosine of x. And we're going to need a couple things to do that. The first thing I'll need to do is take this cubic root of x and, of course, rewrite it as x to some power so that I can use the power rule. I will need to use my newly acquired knowledge that the derivative of the cosine is negative sine of x. And, of course, I'll have to use the product rule, which says we'll take the derivative of the first function times the second function. I'm going to add to that the derivative of the second function times the first function. And I will try to color code this as best I can to make things as clear as possible. So the derivative will be the derivative of this first function. Since I rewrote the cubic root of x as x to the 1/3, I know to drop this power down and then decrease this power by 1. 1/3 minus 1 is negative 2/3. This will be left alone. So the cosine of x just stays exactly as it is. I'm going to add to that this guy's derivative. Now the derivative of cosine, we just learned, is negative sine of x, something we will have to memorize before May of next year. This guy's derivative times the first function, which is x to the 1/3 power. And I'm going to do a little bit of algebraic stuff to clean this up, so it looks a little bit nicer. And I'm going to make a second video at some point showing you how it would look if it were a multiple choice question, how they would make the answer look. But I don't want to do that in this video because it's just really a whole other can of worms we don't want to deal with. But I would say that this is going to be equal to 1/3 x negative 2/3 cosine of x. And then for this part, it is, like traditional, or like to write the algebraic part of an expression first and the trig part second. So I'll usually see this rewritten as negative, put the algebraic part first, and the trig part second. We'll call this the derivative. And now the only other thing I want us to do is to take this original function and graph it on decimals. Also graph this on decimals and compare the two graphs. So let me pause the video while I pull up decimals and show you how that analysis works, so you can see if you're using this rule correctly, and also to reinforce and bolster those skills that are required for comparing a function to its derivative and what you're looking for when you look at that kind of thing. So just give me one hot second. So here I am at my new favorite site, decimals.com. You can see up here I've entered the cubic root of x, which I use an exponential function. There's a way to get a cubic function in there, but just use the fractional exponent. It's the best way to do it, in my opinion. So in green, we have the original function, the cubic root of x times the cosine of x. And then in purple, I've got what I think the derivative is based on the calculations that I had done earlier. I'm supposed to now use these graphs to analyze to see if things make sense. So here's what we're going to do. We're going to look at the green function, which is the original function. And any place this function is increasing, we are expecting the purple graph to be above the x-axis. We expect the purple graph, the derivative, to be positive. And any place this green function is decreasing, we would expect for the purple graph to have negative values, to be below the x-axis. So you can see, here's an area on the green graph. From this point here to this point here, you can see the graph. If you imagine those tangent lines, they're going to be positive, and to be more and more positive, and as they get to this point, they'll be less and less positive until they're 0. And from about here to here, that purple graph is more and more positive and less positive. So far, this seems pretty reasonable. Let's look at another place where the green graph is increasing. The green graph increases from from here to here. This is a weird area. So let's come back to this one. The green graph increases from here to here. So if you imagine those tangent lines, they'll be more and more, the slope will be more and more positive, less and less positive, and then the tangent line will have a 0 slope. So I would expect the purple graph to get more and more positive, less and less positive, and then when that tangent line is 0, the purple line is 0. We can do a similar thing where the green graph decreases. The graph decreases from here to here, and from here, from this x value, where the green graph starts to decrease, and this x value, where the green graph stops decreasing, we can see the purple graph goes more and more negative, less and less negative. So it seems like my work is correct. In this middle area, something, I don't know if unexpected, something that you probably don't expect to see is happening. And what's happening is, right at 0, this graph would have, can you imagine the vertical tangent at 0, what it looks like? Right at 0, that vertical tangent, that, I just said the word, that tangent line ends up being a vertical line. It's a vertical line. You can see it's kind of going straight up and down right as x equals 0. Now, you might remember from freshman year or maybe middle school that if a graph is vertical, the slope itself is undefined. We call it undefined slope. Now let's talk about that for one hot second. When you look at this derivative, we have over here 1/3 x to the negative 2/3, which of course I can rewrite as 1/3 and x to the 2/3 in the denominator. And that means if I plug in 0, the derivative doesn't exist. Because you end up dividing by 0, you can't do that. Which is why the purple graph, the derivative graph, looks so strange at 0. It turns out that for this particular function, f prime of 0 does not exist. Because it makes you divide by 0. Now it also turns out that f prime of 0 does not exist. Because if you trace this green graph, and if you imagine that tangent line, right at 0, that slope is a vertical line. That slope is undefined. So I'm not surprised at all that the derivative is showing this asymptotic behavior at 0. Not really important for our discussion. This is kind of a side note that I wanted to bring to you. But you might see this happen while you do your homework. Really all I care about is in this area from here to here, where that graph is clearly increasing, right? If you can imagine that tangent line, it's some positive, more and more and more and more and more positive, so that slope is vertical, and it's less and less and less and less and less positive. And we can see the derivative becoming positive and becoming so positive it's going all the way off to infinity, and then it becomes less and less and less and less positive until it gets to this point where it becomes negative, and the place where the derivative is negative also matches where the tangent has a negative slope. So looking at these graphs and thinking about them is such a powerful way to really like solidify your understanding of what's happening. You know, imagine those tangent lines. I'm a little bit off topic. Like, this is a little more than we need to worry about. If you got this answer as your derivative, and that's all you can handle right now, that is awesome. That is great. But if you are like, yeah, that was easy, I want to do more, really think about these graphs and what the heck's going on there. So I'm going to stop this video 3 minutes later than I wanted to, and I hope it was interesting. All right, good luck, you guys.